Greetings, the Astro 30 here yet again, and today I'm doing a bit of a different video to the current ones I've been doing. I've got another kit to build. Now this is a silicon chip kit. This is a high power class D amplifier which is capable of delivering 150 watts into 8 ohms and 250 watts RMS into 4 ohms. Yeah, we'll ignore the RMS part. Anyhow, it says the do-it-yourself high performance amplifier boasts 250 watt RMS output into 4 ohms. 150 watt into 8 ohms and can be bridged with a second kit for 450 watt into 8 ohms. Not only does it output high quality sound, it is also rugged and reliable with all sorts of protection built in. Class D amplifiers are also far more efficient and generate much less heat than linear Class A, B and AB designs. The kit includes the PC, which is 167mm by 117, so it's fairly big, with a loaded SMD IC, so the actual main amplifier IC, which is a surface mount device, is already installed on the board, which makes it a lot easier. Heatsink, electronic components for a plus-minus 55 volt DC supply. Now, this should run on a slightly lower voltage, say plus-minus 30. I don't know yet, haven't tried it. But that's the maximum you'd run it on. So you'd need a 40040 toroidal transformer, at least a 300 VA, especially if you're going to be running 2 of these modules. There's the catalogue numbers for the power supply and optional speaker protector kits, which is KC5517 and KC5515. I believe I can still get the power supply from JCar. I can't get the speaker protector, I don't think. That doesn't exist anymore. And there's the catalogue number for the actual amplifier module itself. It's a KC5514. And it's published in the Silicon Chip magazine issues November 2012 and December 2012 respectively. And they estimate around about 4+ hours to assemble it. So I don't know if I want to do a 4-odd hour time lapse of assembling this, because it would take me at least 12 hours to render it, but we'll see what happens. That's just their estimated time frame. But what would you use this for? Well, you could use it for anything really. There is nothing wrong with Class D amplifiers, only the design of the Class D amplifier. There are crap Class D amplifiers, and then there are pretty good Class D amplifiers. How good they are is subjective, and it's really down to personal taste. And I mean, if you can hear nuances on the output, it's a crap amplifier. If you can't, and it sounds just the same as a Class AB amplifier, for instance, then yeah. You could use this as a subwoofer amplifier if you had a subwoofer capable of a peak of at least 250 watts. No problem. But what we might do is get the kit contents open and we'll have a look at what we've got. And I've mentioned JCar quite a few times in a few videos, and if anyone wants to know how to get in contact with them, especially in other countries other than Australia, we've got the New Zealand contact, their website and phone number, the American, Canadian website and their phone number, and the United Kingdom website and their phone number. So I'll just leave these numbers on the screen there for a few seconds whilst I'm talking about nothing. And yeah, you can either log into your browser and look at a few of these links that are here, and or ring them directly. So on first opening the kit, we have a circuit board which is sitting in an anti-static bag, and there's our little SMD IC there. It's using an IRS2092S IC. I'll look that up online in a minute, see if I can find a data sheet just to see what it is. But yeah, that's the heart of the circuit. That would be the main amplifier processing IC. So we'll leave that in its anti-static bag for now. And we've got a heatsink, which we're going to have to drill, which is always fun. But they've included a HH8566 heatsink, which is 110 by 72 by 31, I think it is, that distance. It's the same as the one I've got sitting in the cabinet over there. But yeah, it didn't say anything on the front that there's going to be some drilling required. But if you build this kit, be aware you're going to have to drill a heatsink. And the heatsink holds what I can see from the front picture of at least 4 devices plus one extra cable going to somewhere. But that'll be denoted in the instructions, and hopefully the instructions give you a little plan to drill this, because you're going to have to drill in between fins as well, which is going to be fun. And I'm assuming you're also going to have to tap it, which means you're going to need a tap and die set capable of doing M3 screws. This isn't too bad to tap, but thicker heatsinks can be time consuming and a pain in the ass. So I'll put that to the side. We've got a bag of components here. They give you a couple of rolls of solder, some seal washers. I'm not sure offhand what those are. But anyway, we've got a couple of TIP devices, transistors here. An IC, which is just a TLE207. That can't be right. Yeah, TLE2071 according to the circuit board. I'm not sure what that is either. Probably an op amp. Bunch of resistors and capacitors. Some real large capacitors here, which are Suntan brand. It doesn't say what its voltage rating is though. 275 volt. So yeah, and a bunch of transistors and diodes and stuff. So anyway, Silicon Chip call it the Classic D, the world's first do-it-yourself high-power, high-performance Class D amplifier. 250 watt into 4 ohm, 150 watt into 8 ohm. And a little blurb down there saying you asked for it and now we are finally delivering it. Actually, that's interesting. The background of the photograph of the amplifier module is actually the schematic. That's a nice touch. I like that. So here's our simplified schematic of the amplifier. You've got your incoming waveform, and it's compared against a triangle waveform here in this comparator, and then drives a pair of MOSFETs to generate the PWM pulse width modulation waveform, and then this passes through an LC low pass filter out to the speaker. That's basically how Class D amplifiers work. And just underneath that it says that this diagram up here shows the 2 input waveforms fed to the circuit of the first circuit I just showed you, along with a PWM output, which is VO. So you've got your triangular waveform here on the comparator, you've got your signal input here, your sine wave, and superimposed on that is your digital square wave output. And then the output of the filter will be quite similar to the shape of VS. So the filter should remove both the triangular wave artifact and the square wave artifact. Over on the next page we've got a more complete block diagram of the amplifier. It adds an error amplifier which provides some feedback from the output, reducing distortion. The output arrangement is improved too, with a pair of N-channel MOSFETs instead of a P and N. With that arrangement, the upper MOSFET must be driven from a floating gate supply and a dead time generator, which is this and that. That's the dead time generator, and that's the gate driver basically. And this is used to prevent cross conduction, which would otherwise waste power and increase dissipation. And there's your low pass filter there, which will get rid of the high components, which is the high frequency crap of the square wave and the triangle wave on the output, and only just allow the audio through. And there's our feedback path back to the input of the error amp. So the more we get into it, the more we realize it's fairly involved. This is the complete schematic, and it is quite complicated at first glance. The interesting thing up here is we've got this link 2, which allows normal and inverting. Now, I'm assuming that means you can actually switch the phase of the amplifier. So you can have the output inverted, or you can have the output non-inverted. I'm assuming that's what that's for. And it's not mentioned in the little text underneath the schematic here, but you've also got another link over here, LK1, which is a ground lift. That would be for having inputs that have a negative base ground, such as preamps or single-ended. That just separates that from the main ground, because this is a bipolar circuit. There's not much else to say here, except they're using 2 identical N-channel MOSFETs at the output, which are on that heatsink. And the heart of the whole thing is the IRS2092. Now, on the circuit board itself, they do actually provide extra protection on the amplifier. It provides over temperature protection and over and under voltage protection. So if any fault of the conditions is met, Q9, which is here, will turn on an LED letting you know that there is a fault condition. So I can see right away that the B plus is a 39 volt Zener diode, so that if the B plus is any lower than 39 volt, then the circuit will fail to operate. The interesting thing is it'll operate over the range of plus minus 40 to 60 volt. So right away I'm a little bit screwed, because I can't get anywhere near 40 volt. I can get 30, but because of that under voltage protection there, which is a 39 volt Zener, it's not going to operate any lower than 39 volt. I'm going to tell you that right now. So we'll turn it on and nothing happens. So I need a higher power supply, which kind of sucks because I just got back home, but yeah, I don't know how I'm going to, because JCar don't sell many transformers anymore, and it's getting awfully difficult to find transformers. So how I'm going to get anywhere near 40 plus minus is beyond me, and whether or not this is going to get built today. Okay, so an update to that before I get too involved in building anything is I did look on JCar, and I can get a single-ended 30 volt multi-tap transformer which is capable up to 6 amps, which is an E-core type transformer. I'd have to buy 2 of them, and they're relatively cheap. They're only like $30 each, so that's $60 for 2. I would have to get the power supply that goes with this kit, which is another $34 on top, so for another $94 and plus the $90 for this kit, we're looking at $180 in one day. So this is quite an expensive hobby when you get down to it. So I might go to the toilet, relieve myself, and go back out to JCar and buy the necessary bits. I'm kind of not happy, but yeah, that's what happens. Okay, and a short time later I am back with 2 transformers, catalog M2015. They're capable of up to 6 amps, 100 VA each, And basically all we do is we wire the two secondaries in series with each other in phase, and we'll end up with a 30 volt transformer needed to power the amplifier. So this is the power supply, KC5517. Apparently it has two LEDs which illuminate when power is present on the rails and to assist in slowly discharging the filter caps when power is switched off. You can add additional components which are not supplied to provide a 20 volt power supply rail, which I assume is for the speaker protector module, as well as a plus minus 15 volt rail for optional powering of a preamplifier. Now what am I going to do with all this, considering I've just now spent $180 on all this? Well, I will be making something out of it. Not 100% sure yet. I want to see if I can get the speaker protector online and look at that in a separate video. I don't know if they made a preamplifier for this or not, but yeah, today we're going to concentrate on building the power amplifier and power supply. I'm going to take bits of video along the way. I'm not going to do a time lapse of the whole thing because it's just going to take a lot more effort to do that, plus take a lot longer to edit. Now I'm just going to quickly look up the IRS, Internal Revenue Service, the IRS 2092S IC and the TLE 2071, which I believe the TLE 2071 is just the comparator IC, but I'll have a quick look. Okay, so the IRS 2092 is a protected digital audio amplifier. Its features is an integrated analog input class D audio amplifier driver in a small 16-pin package. Floating inputs enable easy half-bridge implementation, programmable bidirectional overcurrent protection with self-reset function, programmable preset dead time for improved total harmonic distortion performances, start and stop click noise reduction, that means when you turn it on and off, high noise immunity, plus minus 100 volt ratings deliver up to 500 watt in output power, operates up to 800 kilohertz, ROHS compliant. Typical applications are home theatre systems, mini component stereo systems, powered speaker systems, general purpose audio power amplifiers. I'm not going to go too much into the data sheet on this. If you want to look it up, you are more than welcome to. But basically it's a digital audio amplifier front end PWM driver. So that's all that IC is. And apparently the TLE 2071 is a Excalibur low noise high speed JFET input operational amplifier. So it is an op amp, not a comparator. So the one used in this kit is a mono op amp or single op amp with JFET input, and you've also got an offset null on pin 1 and pin 5 respectively to adjust the offset null, or offset, DC offset I should say, of the op amp. So basically it's just a low noise high speed with JFET input single operational amplifier, and it's no more to say about that than that. Okay, so it's time to start thinking about constructing the power amplifier module, mounting it in my tool, and this funny looking component here that I was saying I didn't know what it was before, that's actually the inductor, L1. So that's what I'm going to do, is I'm going to build the circuit board up now. I'm going to put every component on, bar the ones that mount to the heatsink. That one with the wire on it is just a ground, so you ground the heatsink. Yeah, it's pretty real straightforward. It's just mount all the components on the board, start with the smallest first and work your way up to the largest components. Being mounted in my tool, I can choose whichever components to mount I want. It doesn't really matter what order I do it in. So yeah, I'm going to get to doing that, and then we'll move on to the power supply, etc. And it also helps to read because you can change several components on the circuit board if you want to run at lower voltages. In this case, plus minus 35 or plus minus 25. So yes, it can run on lower voltages if you make component changes. So I just went out and spent 90 bucks, we'll say, for no reason. But then again, I want to build the circuit the way it was originally intended. Now, just as a quick tip as I'm soldering in resistors, you'll notice on this side that solder has come through the plated through holes on the other side. This is a double-sided circuit board. So just simply doing this till it's soldered is not going to allow the solder to flow through to the other side. So with this, I worked out, hold it there for at least 3 seconds and then release. Like magic, it's flowed through to the other side. Of course, if you have already soldered it once on here and it hasn't come through here, you can always just touch the soldering iron on this side with a little bit more solder to do the job, but it's quicker and easier to just let it flow a little bit longer on the other side. Okay, all the resistors are installed with the bands the same way around to keep the electrons from falling out. No, anyway. In the resistor section of the plastic bag here, we've got 2 leftover components. This blue thing, which is marked TDC247, I'll get to that in a minute, and this 2K 10-turn pot. Now, there is a specific way around that you need to put it so that the clockwise position is in the correct direction, so when you're turning it, you're increasing it and not decreasing it. It may seem unimportant, but there is a specific way of putting it around. So the clockwise position is over here in the footprint for VR1, and there's the little screw terminal. So clockwise is opposite the screw. So we would put it in this way round, which doesn't quite fit in the board with the resistor soldered there, because the solder is holding it up a bit. See? So that's probably a little bit bad design on Silicon Chip's part. But anyhow, and this marked TDC247 is actually a negative temperature coefficient thermistor, and that needs to come into contact with the heatsink, and there's a specific step which is outlined here in figure 19 for the thermistor clamp. It's made from a 6.4 millimeter splayed lug, and you have to bend it around about here where the terminal is at 4 millimeters at a slight angle, so that the thermistor body can actually come into contact, probably on this side more likely, and that's the screw side, with the heatsink. So that step I would do last after I have mounted the heatsink, and the thermistor just mounts here. But of course it needs to come into contact properly with the heatsink, so you might have to bend it at a slight angle. Probably apply a little bit of heat transfer compound just to make sure there's good thermal conductivity between the two. But for now I'm going to leave this part off. And with the heatsink, they say if you want to mount this in a 1 unit rack mount case, well, you're going to have to cut this heatsink down to 30 millimeters high, which is going to be very tedious and time consuming. If height is not a problem, you can leave it like that. And in fact, I'm going to leave it like that, even though it's excessively large. But in the end, this is probably going to be mounted in a 3 unit rack case when all is said and done, just because, well, I can. Anyhow, getting on with the construction, I'm going to solder this variable resistor in, and I'm going to look for the PCB pins that need to go for all the connections here, and yeah, then move on to capacitors, and then finally the semiconductors. I'm going to mount all the LEDs on the board. Why not? They're there. They don't really need to be at the front panel, although the protect LED probably could, but that only detects when you're going over voltage or under voltage. So right now I'm going to move on with that. Now you may notice on the board when doing the capacitors, things marked as 100N2 times 2 or x2. There's also 470 nanofarad x2 over here. That just basically means these type of capacitors. See at the end here it's marked x2. And this one is a 474K, which is a 470 nanofarad, and it's rated at roughly 275 volt. So that's what they're talking about there with the X2s. So for instance, my 100 nanofarad X2 would go there. There is another one on this board somewhere, which I haven't quite located yet. There is 2 of them, but I can't see the second one at the moment. But that goes there, and the 470 nanofarad goes there. That leaves this one left over, which doesn't appear to go anywhere. Oh, there it is. It's right up by my clamp. So I might have to just move the board over a bit to get that in there. But that's basically all that means. But having figured that out, we can move on. Okay, that's all the capacitors installed. Capacitors, and as we can see, the board is starting to take shape. It's taken me about an hour and a half to get to this point. So yeah, their recommended time of 4 hours plus would probably be very accurate. You've got to take your time. The most time consuming part will be doing the heatsink, as I said before previously, I believe. Just one problem with the capacitors. Some of them don't quite fit the footprint properly because of the size of the capacitor compared to where it's placed on the board. I mean, this one in particular, I had to mount slightly proud of the board to clear that resistor because the resistor's in the way. And the same over here with these 100 microfarad 25 volt low ESRs, that 1K 1 watt resistor is in the way. So I've had to raise it up above the board and above the resistor slightly to clear it. You'll also take note that I've got between my 1 watt resistor devices here about a millimetre or so of clearance between the board, as I always do. Anyway, typical faults aside with components not fitting the footprint, they always do, I'm now left with the semiconductors and that large inductor, plus the fuse clips, the input connectors, and excuse me, the PCB pins, which I haven't located quite yet. Plus there's 2 headers to install, well actually 3 really, one here, one there, one there. I don't see any other headers anywhere else. They do give me a header with, I believe, 8 pins on it, maybe 7. 1, 2, 3, 4, 7. So that's 2, that's 5, that would make 7. They're just basically jumper connectors. Well, these are jumpers, that's actually for something else. Oh, there's another one over here, yeah, LK3. So there's 4 of them, so I don't know if I've got enough for that, unless there's a specific connector to go here, because that footprint looks like a connector. Anyhow, I'm going to have a break, have a smoke, maybe take a piss, and then I'll move on to the diodes and LEDs and that op amp there, and yeah, we'll progress slowly. Just with this sort of thing, take your time, make sure you orient components correctly in the correct places. If you're unsure of these 5 band resistors here, of what their value actually is because you can't read them properly, and even if you can read a 5 band resistor color code, doesn't mean to say you can actually read the colors properly on some of these resistors sometimes. One color may be mistaken for another. So it's always a good idea to stick it on a multimeter just to double check before soldering it in. Because there's nothing worse than soldering the bastard in, plugging it in, either something going bang or the circuit just not working altogether, and then being frustrated and thoroughly pissed off as to trying to figure out as to why. So anyway, just keep that in mind. As I say, I'm going to have a little bit of a break from this, and I'm going to continue shortly. And yep, I found it. LK4 is one of these. These are always a pain in the frickin' ass to wire the plug at the other end, which they did not supply, so you have to buy your own plug. But yeah, Not sure offhand what that is for yet, but we'll find out during later in this video. But that's what that's for. Okay, with the fuse holders in and the connectors, I've just realised that they haven't given us any PCB pins, which is kind of handy. So I found some leftover PCB pins from another project. Hopefully I've got enough here. I don't really want to have to go down to JCar again to buy any more, but the easiest way to solder these in is to do it from the top. Just give it a little bit of heat there for a few seconds and it will go through to the other side of the board just fine. Well, I've got all the PCB pins in that I have. There's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 I think, something like that. They're basically just test points anyway, so they're not really all that overly important, but it's always nice to have, like, you know, somewhere there to stick a probe and keep it stuck there, not rather than try and, you know, have 3 hands to, like, you know, measure shit. So would have been nice if they had supplied us with the PCB pins, but they didn't. Albeit they're not really needed for the circuit operation, they're just there to assist in testing it. Anyway, I'm going to just touch up the solder on the end of that resistor, and I'm going to move on now to the semiconductors. Yeah, well, I've got all the Xeno diodes in now and the silicon diodes. Yeah. I'm moving on to the LEDs. Now they say there are 2 LEDs. One is blue, one is red. Well, LED 1, which is here, right there, the run LED is supposed to be blue. Now, the other one, LED 2, which is the protect LED, is supposed to be red. Now in this kit it's pretty obvious. One's got a red lens on it, and the other one is a clear lens. So the clear lens is a blue. But if these were both clear lens, how do you determine which colour's which? Well, most multimeters in the diode test mode have enough forward bias current to turn these LEDs on when you're testing them, so you can actually see what colour it is. So if we just move the jig out of the way for a tick, and I'll grab this blue LED and my multimeter, and I'll set it to the ohm scale, diode scale, and select the correct mode, which is diode test. The longest lead is the anode, so this is going to be a little bit awkward to do one-handed here, but you'll notice that by touching it in the correct direction in diode test, we can see that that one is blue. Now if we take the same theory with the red LED, we know it's red, but again we put the long lead on the positive and then the black lead on the negative. It's just lighting up, but you can see that it is red. This is a very low current LED, so that's why it doesn't glow as bright as the blue. So we now know which LED is which, if you didn't before. Now we can install those in the board where they go, remembering LED 1 is the blue one, the run one, and the protect one is LED 2 over here. And yeah, I'll continue on with mounting the rest of the small signal transistors, and then we're up to the hardest part, which is the heatsink, and this circuit is almost complete. Well, Progress is my middle name. The Progress Astro 30. The Astro Progress 30. No, that doesn't sound right. Anyway, I've got all the transistors installed bar one. I missed one, and it doesn't even appear to be in the kit, which is depressing. Huh. I see it. It's still in the plastic bag. I'm missing a 327 over here, which I've got in my hot little hand. I'll put that in. But I'm up to doing the hardest part now, which is the heatsink. I'm mounting all these components to the heatsink. So I'll install this transistor that I forgot, and then I'll move on to drilling tapping the heatsink, and it's about 2 o'clock now, I think. Now it's actually 2:30, so I've spent the best part of 2.5 hours doing this, and this is how far I have got, which may not seem very far, but remember the kit did say 4+ hours, so it's not something you can rush. I mean, you can if you want, but you're not going to be very successful in the process. Anyway, that transistor is now soldered in. I can clean up a bit and move on to drilling and tapping the heatsink. There's another resistor that's not quite soldered properly at the top. You get the odd one or two. I mean, for all intents and purposes it doesn't matter, but it just looks cleaner if the solder has gone right through to the top as well, in my opinion. You can't do much about undercapacitors because you can't see them. But one thing with these jumpers, now I'm not going to be using ground lift, so I'll just have to look at the circuit here for a sec to see what we've got for that. Link 3 actually puts the protector into protect mode, so that's that one there, so we leave that one open. For floating ground or ground lift, we don't want that open, so that has to be closed, otherwise that puts the 10 ohm resistor, is it 10 ohm? Yeah, 10 ohm resistor into circuit. I think it's, yeah, I got it the right way up the first time. So we plug that one off. And I don't want it in inverting mode, so I'll be putting it into normal, so that goes on that one just like that, just so I don't forget to do that and go to test it and something doesn't work. So those two jumpers are installed, so now I can move on to the heatsink. Now with the heatsink they do actually give you a drilling guide, which is handy. Now this is assuming you've cut the heatsink down to 30mm, so just make sure you're measuring from the bottom of the heatsink up. So it gives you all the measurements, where you're to measure in and where to drill the holes. One's a ground point, one's for the thermistor clamp, and these 3 are for the transistors. So they should sit right, if this was to scale, yes it is, those holes should sit, let's try that again, those 3 center holes should sit right in the center of the heatsink. I know you can't really see that very well, but yeah, they sit right in the center part of the heatsink, so that's not too bad. These other holes have to go right in the middle of the fins, and they do line up if you measure it correctly, so take your time when measuring that. As they say, measure once, cut twice. No, measure twice, cut once. They also give you in the kit a piece of heat shrink and a piece of link wire, and plus one of these transistor TO3 transistor tags. That's for making the ground point to go up from this point on the board to the heatsink, to ground the heatsink. So the idea is you put the heat shrink over there to stop it shorting on anything, heat it so it shrinks around it, solder this on one end, and then solder the other end in the board. I would permanently solder it in, but yeah, that's how that would work. Here's display terminal that we've got a bend for the thermistor. It's already bent at a roughly good angle there as it is. All I need to do is then just grab a pair of bullnose pliers, which is what I might do now. And I'm going to take and guess this. I'm not going to be super accurate. I'm going to say that's about 4mm. And I'm going to bend him over like that. It's probably a bit far. And that should be sufficient for this thermistor, which I haven't soldered in yet. Oh yeah, that's perfect. That'll just sit flush up against the heatsink just nicely. And a bit of thermal compound behind it. Bob's your auntie. So let's stop playing with my penis and move on to doing the heatsink. But I'm going to have another little break for a while and contemplate the universe as well as my navel. And then, yeah, we'll move on to putting the heatsink on, the last devices, and actually get about, well, we can't test it until I build the power supply. But the power supply board should be a shitload simpler than this. And if you're going to do stereo, remember you've got to build 2 of these. So it's quite time consuming. As for what LK4 over here is for, I might find that out now because that's kind of intriguing me now. Oh yeah, that makes sense. LK4 just connects to this protector circuit, which basically all it is really isn't all that complicated. It's you've got your 2 protect inputs coming in from the boards, LK4. It's going through an optocoupler, basically into, well, the relay driver over here. So I assume in a fault, this optocoupler will allow this gate here on this STP16NE06 to be brought to, well, ground in this case, basically removing the relay drive. Yeah, and that's before I even read the text down here. So if either fault input is triggered, it pulls the gate of Q10, which is that transistor driver there, low via its associated optocoupler, either one of those 2 there, and a 1K resistor. It pulls it low. This will turn off RLA1, which is up here, disconnecting the speakers, and lights LED 3. So LED 3 here is just the protect LED, which would be mounted to the front panel to let you know that there is an actual fault with the amplifier. So that is a very simple loudspeaker protector circuit that I have ever seen. It's not overly complicated. Should be relatively cheap to buy too. I'll have a look online later. But yeah, it doesn't use any transistors or any DC detectors like that to do the work. It's just used 2 optocouplers, which is kind of nice. Anyway, that's detracting from what we're actually doing, which is finishing assembly of this. I have no idea how long this video has been going for, probably 100 million years. I hope you're enjoying it, and fine, if you want to buy this kit, you can probably buy it easier online than you can at JCar. But I can't remember if this is available at Alltronics. It probably is. But yeah, I hope you're enjoying it and getting some information out of it if you're choosing to build this kit. It's been fun so far. Very time consuming, as I said, and I'm really kind of putting off doing this part because I can't be bothered. But I've got to do it, and I don't think these holes up here are tapped because there's M4 screws that go in that, or they're either M4 or M5. I don't believe those holes are tapped to allow the bolt to bolt it up. No, they're not, because here's bolts to mount the heatsink to the board, and that's not threaded. That's not going to thread, and I'm going to have to add some threads in that by tapping that. Fun, more work. Great. Alright, break time, moving on. Well, fuck my life. After all that, I found the bloody PCB pins. They were in the kit. I just cut them off at some point. This is where the resistors went. And these were right at the front and I didn't see them. I was about to throw some stuff out, so I found the PCB pins. Yay. Okay, the holes are drilled. I've massaged the measurements for these from that side, the left hand side there, just so they're directly in centre with the fin holes. They're tapped to 3mm M3. These 3/16 were 20mm long screws. I found you don't actually need to tap a hole in here. They will just grab and bite in there nicely and start doing up. So it's all deburred. So now all I've got to do is bring the PCB back in, and well, it goes something like that. So I might start with taking it out of the jig. Might help matters quite considerably here, and then turn the heatsink upside down, and then Well, I will try and get that screw started as straight as possible. And as I say, with a bit of effort, it will do up. What I might do to speed the process up is use an electric drill. There we go. A little bit of, not too much damage to the heads of the screw, but yeah, it did go up there. That's nice. So now I can start by losing things on the floor. Mounting the transistors to the heatsink with the appropriate isolators in the correct places, and bang into the light and solder them in. So that's what the module looks like so far. It's getting there. So what they want you to do is they want you to take a device, one of these sill washers, which is the greaseless kind. So the washer, device, and then there is a little bushing which goes on top of the device like that, and then you pass the screw through to the heatsink. Which they haven't actually provided us this with any M3s. Oh yes, they have got 4. We need 5. So there's one missing somewhere. Well, that's kind of handy. Don't know if that screw is actually going to be long enough. Oh yeah, just. I'm not going to use those. I'm going to use 10mm ones because I think they're way too short. So I'll start with the transistors, as I said, and yeah, then we'll worry about the grounding later, and the thermistor. So yeah, I'll use a 10mm screw instead. So I would strongly suggest mounting and securing the device first before soldering it. Penis. Alright, no, don't need to over tighten them, just so they're torqued. It doesn't matter really if they're slightly crooked because your measurement was slightly off. As long as it fits in the hole, and it doesn't matter if they're slightly higher than each other, as long as there is enough lead sticking through the bottom of the PCB to solder to, it's fine. And this is why I say install the devices first and screw them to the heatsink before soldering them, because after you've soldered them, it makes it awfully difficult to move them. So now that they're in their respective holes, it's amazing that you're going to get like 150 watts out of these tiny TA220 MOSFETs here. But yeah, that remains to be seen. So there we go, the transistors are now soldered in, and yeah, enough of the solder's come through on the other side, so I need my side cutters wherever they've buggered off to. Must admit, these boards that are made by JK and Ultronics are pretty well made. But that's the modules so far. The next thing is, remember this guy? Yeah, well that's got to go in here. And this is the reason why I said don't solder it yet, is because we need to get a makeshift clamp to clamp it to the heatsink. So we need to first get our height before soldering it. So what I'll do is I will use only a 5mm screw for this. I'll prop this up on the solder and put the clamp in. Now I'm assuming this is the way it's supposed to be assembled. I can't see it mounting at an angle because it wouldn't work. So we screw this all the way down till it bottoms out on the heatsink. Trying to keep it as straight as possible, I guess. Right, so that's bottomed out. The device is now sitting roughly where it needs to be. So I can turn him over. And it shouldn't matter which way around this is soldered because it is just basically a thermal resistor, so it should have no polarity. And we solder him in. So that now should be in the correct height and orientation. And basically now we can back that screw out and move that clamp out of the way for a second. And I'm just going to give this the best possible chance to have good thermal conductivity once I don't slip off my chair by applying, not that they say to do this, but it's not going to hurt it, applying a liberal amount of, it's probably way too much, but you get the idea. It's like someone's come on my heatsink. So that'll give it some thermal conductivity between the heatsink and the device. And plus, when building stuff like this, especially with heatsinks, I like making messy stuff like this. It's fun. It's all part of the fun and the building experience. So there's our module. It's almost complete apart from the ground for the heatsink, which is just this piece of wire, and it probably doesn't need to be this long either. So I'm just going to eyeball this up and say that I reckon if we cut off a good 15 millimeters of that heat shrink, maybe 20, that should be plenty. So that's what I'm going to do, is I'm going to cut off about 20 millimeters, which is basically cutting it in half. I'll keep the half. I'm going to make this my ground, so I'm going to put it in the center of the wire. Heat it with a lighter like that. You can use a gun. Be careful because this wire is going to start getting hot. So that's sufficient enough. It's just basically to stop it from shorting on anything. So what I need to do is I need to first mount it in the board somehow without it falling out. Put it on top of the heatsink like that, might help it stay there. And then I can solder him in like so. That should be soldered in. Don't really have to trim that, but I'm going to. Okay. And then we take our enormous penis, wherever that's gone. I mean our little eyelet thingy. This thing. And we place it over the end of that. And we gotta basically get it to a point where, probably coming out the front would be better. I might put a little bit of a bend in it. Anyway, it's built, so the next thing would be a good idea to build the power supply. Now, they reckon that this power supply module should take up to 90 minutes to build. So, that's the next thing we're going to look at. Unfortunately, I'm a bit spent at the moment, but yeah, you get that. Shit.